far so good. Okay, let's add to this then. So we just talked about the harmonic series, and when I showed you the harmonic series diverged, I actually compared it to the function 1 over x. I'm just going to graph it again real quick. Y equals 1 over x. And I looked at from 1 to infinity, this area in here. And we talked about, we already had done the integral of that way back when in chapter 7 and found that it diverged. And then it turned out that the series also diverged. Series and integrals are tied hand in hand almost. They're almost identical. The only difference is that series always count by ones. You go from 1 to 2. You can't stop at 1.5. And functions are continuous. You can have 1, 1.5, 1.3, whatever. But the idea is the same. So what the integral test tells us is that if you change your series into an integral and that integral converges, then so does your series. And if you turn it into an integral and your integral diverges, then so does your series. So here's the notation that I have written on my notes, which are lots of it. If, so you want to put this at the top of your notes there, I left you that blank space. Notice it's an integral from 1 to infinity. Why do you think it's 1 to infinity? Yeah, why does it start at 1, the integral? Where does series usually start? At 1, all right? So if this converges, then the series n equals 1 to infinity of an converges. This is important that an is the same as f of n. We're changing the function notation into the series notation. So like when we did 1 over x, this integral diverged. That's the 1 over x, that's our function. And now the series was 1 over n. It's the same reasoning. So if the integral converges, so does the series. And guess what happens if the integral diverges? So does the series. So sometimes it's not geometric. It's not the harmonic. I need to write this before I can talk, so I'll write something wrong, sorry. So you have a series. It's not geometric, so you can't decide that way. It's not the harmonic, so you can't do that way. And maybe you've done the divergence test and you got 0. What happens if this limit is 0? When you're doing the divergence test? If the limit of your terms approaches 0.
Converges?
No. The divergence test only tests for divergence. If the limit of the terms approaches 0, then we don't know. We know nothing. So let me give you my example. If you're sitting in this class, you're an LMC student. If I find someone who's not sitting in this class, it doesn't mean they're not an LMC student. They might be. It's not one or the other, right? One doesn't necessarily imply all of everything else. So if this is 0, if your limit of your terms is 0, that means your series may or may not converge. We need to figure out what it does. We say that divergence test is inconclusive if it is 0. If it's not 0, we're sure. But if it is 0, then now we got to check to see what happens. I'll be using the divergence test all day to do some quick checking along the way. This notation make sense? You've got to ask notation questions. Okay, let's look at example 1. Example 1 wants to know if this series, n equals 2 to infinity, of 1 over n ln of n, does this series converge or diverge? By the way, what does it mean for the series to converge?
It's approaching one specific term.
What's approaching one specific term?
All the terms that, or the function as it's approaching infinity. It's approaching.
The limit of the
So you guys are all kind of on the right track. You said a word that I was needing though, Zach, the sum. So it's not that the terms are approaching something, it's that the terms are adding up to a finite number. They add up to a finite number. Remember I ripped up the papers and they all added up to 1? They might be adding up, they might be approaching 5, but that means I'm adding 5 forever, then that would not be convergent. So convergent means the terms add up to a finite number. So the first thing I'm going to do anytime I'm asked to do a check to see if a series converges or diverges is I'm actually going to use the divergence test just to check, because if it's not 0, I know I'm done. Now, a lot of times I do it in my head, because then I know if I have to do more work. But we really want to say what happens to these terms in the long run. What happens to these terms? If I put a really huge number in there, like 4 billion, I have 1 over 4 billion times whatever the natural log of 4 billion is.
Getting close to 0.
It's going to be close to 0, right? It's going to keep getting smaller and smaller because you keep bigger and bigger denominators. So this limit is 0. So that tells me that when I start adding these terms, the first one, the second one, the third one, eventually they're really tiny. They're so tiny they're almost 0 eventually. So what does the divergence test tell me? Inconclusive, thank you. Divergence test. I'm doing a divergence test here. If it was not 0, I would know it diverges. If it is 0, it's inconclusive. Can't say that enough. This means there's some hope that it could converge, but I don't really know. Think it's geometric? Geometric? 1 over 2 ln 2 plus 1 over 3 ln 3. Think that's geometric? Am I always multiplying by the same thing to get to the next number? Definitely not, right? The ln, so it's not multiplying. I'm not even multiplying over here. There's no common ratio there, so it's not geometric. So it's not geometric. The divergence test doesn't tell me anything. Is it the harmonic series? Harmonic series looks like this. Does it look like this? No, it's got an ln in it. And, or we could maybe start doing partial sums, but partial sums with natural log, that's going to be a mess. So I don't like any of our techniques, which is why I'm now going to use what we call the integral test. I'm going to integrate this, pretend it's a function. So we're going to take that series, turn it into a function. We're going to integrate from 1 to infinity. 1 over x ln x dx. Just turning my general terms, where'd they go? My general terms into a function, yes.
Wouldn't it be from 2 to infinity though?
Oh, yes it would, thank you. It's important that it start at 2 in this case because the natural log is 0 and it would be undefined at 1. That's why they started at 2. If you plug 1 in there, it's undefined. Thank you for catching that. Otherwise, I would have found that when I went to evaluate this. So now the question is a review of chapter 7. Does this integral converge or diverge? How do I do that? Improper integral, it was called. Like from February sometime. Oh, man. Yes.
Couldn't you rewrite the 1 over x to make it a multiplied times ln?
Well, the ln x is still on the bottom though, but I could. I could write it this way. So the ln x still has to be that. That's okay. The main thing we're looking for here is, oops, I keep changing that to a 1. That's a 2. Is we change that to a b, and then we take the limit as b approaches infinity after we evaluate that integral. Because we need to have numbers here and here to evaluate this integral. So we're going to do this part first. And then we'll take the limit when we're done. Jogging your memory a little bit. So now we have to do this integral. Suggestions on how to approach that integral.
The UDV one?
It could be integration by parts, but before I'm going to try integration by parts, there's one I always like to try first because if it works, it's so much nicer.
You saw?
Let's try U sub. Why should I try U sub, other than when it's nice it's worked out easy? What makes this one an obvious U sub, yeah, Evelyn?
The derivative in the equation function, I guess.
Right, the derivative of ln x is 1 over x. It's right there. Remember, the derivative of a function is there. That's a really obvious U sub problem. So we could use u equals ln x, then du is 1 over x ln, 1 over x dx, excuse me, 1 over x dx. So this part right here, that's my du, right? And this right here is what I chose for u. Yeah. So I'm going to rewrite it then. The limit as b goes to infinity of 1 over u du goes here. ln of 2, ln of b, because u is ln of x. Still okay? All the stuff we've learned piled into one problem. What's the integral of 1 over u? ln of u, right? Limit as b approaches infinity of the ln of u, evaluated from ln of 2 to ln of b. That's the limit as b goes to infinity of the, get this, the ln of the ln of b minus the ln of the ln of 2. That's fun. So as b approaches infinity, this is just a number. I can punch that into my calculator, the natural log of the natural log of 2. That's just a number. I'm not worried about that. So I'm really concerned with what happens here. What happens to the natural log function as you approach infinity? It's divergent. Yeah, the natural log function looks something roughly like this. As you head out towards infinity, the natural log heads towards infinity. So this part right here heads to infinity. And then I want the natural log of something infinitely large. So that means this whole thing is approaching infinity. Minus a little tiny number of some sort. What'd you say, Joseph? Yep. Equals infinity minus some constant. Still approaches infinity, right? Because it keeps getting larger and larger, which he says is divergent. So this integral diverges. That integral adds up to an infinite amount of area. What does that tell me about this series? It diverges as well by the integral test. So we have to do this integration, do all this stuff for review, find out what happens, and then we say that the original series diverges by the divergence test. Oops, not the divergence test, by the integral test. I'm thinking of my next thought already. So this is another example where the terms were approaching zero, but it still added up to an infinitely large sum. Adds up something that keeps getting bigger and bigger and bigger. Even though the terms are getting really tiny, they're just not getting tiny enough in the long run. They need to get tiny faster so that they're negligible. Questions? Notice I wrote the word diverges twice. That's important because this here, this diverges was talking about this integral. All this was telling me what that integral does. That integral diverges using techniques of integration. And then the integral test tells us, well, since that integral diverged, now we know our series diverges because we use the integral test. You're always going to be asked to explain which test did you use and why did you get to that conclusion. Because a lot of people will do all this and then just circle the word diverges on their paper and not write this. You showed me the integral diverged, but I don't know that that means you know that a series diverged. You were doing an integral. You need to make sure your notation clearly says what it is you're finding. Some of you have this deer in the headlights look right now. I need to know if I can help that or not. Anybody want to ask a question? Anybody just want to whine about something? Yes, sir.
Where'd you get the ln2 from?
From u was ln of x. So if x was 2, then u is ln of 2. And when x was b, u is ln of b. We're just changing our bound using our u sub. Because these are x values right here. Because that's a dx. So these have to be u values. So that's a du. Other comments, questions, or whining? Whining's allowed. No whining? You want to whine? He's thinking about it. He wants to, he just doesn't want to admit it. It's okay to whine, and then you gotta shake it off and ask a question. Okay, let's try another one then. I keep putting my notes down and losing them. Okay, that was example 1A. There's a note underneath that one that says we must make sure that the requirements of the integral test are met. The requirements I didn't write down, they're up at the top of the page. Your function has to be continuous, positive, and decreasing. Here's an example when we did earlier. This is a positive function, all of our values are positive. It's decreasing, right? And continuous, there's no jumps in it or anything like that. If your function was kind of strange and maybe it went here, and then it jumped to here, and then it increased and did all this other stuff, there's too many things that could change the area underneath it. So if it's not decreasing and approaching 0, it's not going to work out. There's very rarely do you have a function that looks like that, so it doesn't happen too often. And by checking this, you can see that those are approaching 0, which means they must be decreasing. Okay, let's look at example 1B. That was 1A. This is 1A. Let's try 1B. B now has this series. This one starts at 0. 0 to infinity of n e to the negative n squared. We want to know if this one converges or diverges. I'll take suggestions. you wanna set up an integral?
Yes.
We'll go straight to the integral test? I like that, yeah, Evelyn? You're good?
Yeah.
Okay, sure, let's go straight to the integral test. So integral from 0 to infinity, because it has to match our bounds here. X e to the negative x squared dx. And he wants to do a u sub. Notice I didn't start with the divergence test. You didn't want to, it's okay. We don't have to. It would have been 0 anyhow, which would have told us nothing. So what's u gonna be?
Negative n squared.
Negative x squared. So du equals
Negative 2x.
negative 2x dx. Yes, sir.
Do we have to switch our hands with x's?
So this is gonna be e to the u. What's gonna happen to the x dx? Negative 1/2 is gonna come the other side, right? Divide by negative 2. Divide by negative 2. So this is gonna be a negative 1/2 e to the u du. What's down here? Substitute in for x. Negative 0 squared. Still 0. Careful up here though. It's gonna be negative infinity, right? See how it's negative of x squared?
Can't we do it because it's not met by the requirements?
I couldn't hear, can't do it because
Because it's not in the requirements, because it's not positive.
well, the function has to be positive. This function's positive.
Okay, I just want to double check.
Yeah, the function is positive. So we did a u sub. Looks like something I can integrate. I can't integrate it with infinities up here though. Yes?
Why is it negative infinity not positive?
Because it's negative of x squared. So if you put an infinitely large number in there, infinity squared is still approaching infinity, but now it's the negative of that.
And you do double it, make infinity be.
Right, and then make that top limit b, it's gonna approach negative infinity. B approaches negative infinity of the integral from 0 to b of e to the u du. What's the integral of e to the u? E to the u. So I have negative 1/2 e to the u evaluated from 0 to b. There's no equal sign there, sorry. So then it's gonna be the limit as b approaches negative infinity of negative 1/2 times e to the b minus e to the 0. Cleans up nicely there. E to the 0 is just equal to 1. That's just 1. So now I have this. The limit as b approaches negative infinity of negative 1/2 e to the b minus 1. What happens to this term? It approaches 0. Why?
It's 1 over e to the nth power.
It's negative infinity. So if you want to think of it graphically, the e to the x function as you go to the left, right? Negative infinity is approaching 0 out here, if you think of it in terms of a graph. Or if you think of this as e to a negative exponent, what's a negative exponent do? Flips it upside down, right? So you got your infinity in the denominator. So this term is heading towards 0. either because the graph's approaching 0, or because you're looking at the negative exponent. So this equals 1/2. What does that tell me? What does that have?
Convergence?
Tells me it's convergent. It tells me that this area that I just drew right here, from 0 to negative infinity, this area right here equals 1/2. That's what that tells me. If I know that that area equals 1/2, then we know it converges. The integral converges to 1/2. This area from 0 that way is equal to 1/2. And this integral is the same as the original integral. We drew this picture to be the same, different shape, but same area. We know they're equal. Am I done? Feels like I'm done. Just looking for the right word. The series. So Jamie's saying is now I have to actually talk about what happened to the series. The question was, does this series converge or diverge? We just found that this integral converges. Yeah, so therefore we have to say the series is convergent using the integral test. Therefore, you guys ever seen the therefore looks like this? Therefore. It's like if you're done proving something. Therefore, the series n equals 0 to infinity of n e to the negative n squared converges by the integral test. Yes, Evan?
Why in the other problem we did, the first thing you wrote was like how the limited b approaches infinity, and then we wrote this one kind of like after we.
Because his suggestion was to do a u sub, so we did the u sub first, but we could have written it with the b and then done the u sub. It would have ended up in the same place either way.
Oh, it's still been.
Yeah, been the same thing. The main thing is you can't integrate it until you've converted this infinite limit, whichever, whether it's positive or negative, until you convert it into a b. So you could have done it earlier or later,
Okay.
just before you integrate. Do you think maybe you guys should try one? Do I have one more for you to try? Yeah, I want you to try example 2A, and then we're going to talk about it another way in a minute. Try example 2A on your own, see if you can get it. See if you can write it out, answer this question. Use the integral test for 2A, and then we'll talk about what it says up above there. I'll write 2A up here. Your little brain's moving. 2A. Was it 1 over n to the 7? Walk away from it. Yeah? 1 over n to the 7. Determine if that one converges or diverges using the integral test. See if you can do it. Work together, ask me for help, and then we'll talk about the shortcuts for those. It is, huh?
This is how you register.
one over infinity is 0. Negative over 6 times negative 1. Let's see.
Okay, in the interest of time, I filled in some of the blanks that maybe you still have. So if we're doing an integral test, we're changing it into an integral, integrating from 1 to infinity. I rewrote it as an x to the negative 7 just because it's easier to integrate that way. Introduce the limit as b goes to infinity because we can't integrate and evaluate without a constant there. Integrating x to the negative 7, it's x to the negative 6 over negative 6. Plugging in my endpoints, and simultaneously I put in the, I changed my negative exponents to positive, so see how the x to the negative b, oops, b to the negative 6, excuse me. So b to the negative 6 is 1 over b to the positive 6. Took care of my negative exponent. Here when I plug a 1 in there, 1 to the any power is just 1. So that's why it's 1 to 6. What'd you say?
So it should be the 6 like
Yeah, and my b's and my 6's all look the same. Here, you make this one more straight. There, is that better? Oh, my b look better now? Okay. And then if we take the limit as b approaches infinity, because the b's are the denominator here, this term goes to 0. So the whole thing goes to 1/6. Which tells me what about this integral? It converges. This is a convergent integral. Convergent integral. And if the integral converges, then what do we know about the series? It converges by the integral test. 1 over n to the 7. Now that's a lot of work to do the integral test every time. I agree. So we have some nice shortcuts. I wrote them over here. I wrote one over here if we're going to talk about what it is. I added to our list that we talked about earlier. These are everything we knew before we started today. We've done the integral test. Now we're going to talk about something called a p-series. Before we do that, I need to jog your memory and go back to the page we skipped last time. Back on page 118 of our notes, right under where it says geometric series, I said this should be in the next section. We'll come back to it. We're coming back to it. It says, recall back in chapter 7, we learned that anytime you're integrating a function like this, it converged if p was greater than 1. Oops, I answered my own question. It converged if p was greater than 1. Do you remember why? Do you remember it's been a while since we looked at those? What if p equals 1? What if p equals 1? What does it look like?
Harmonic series.
Looks like the harmonic, right? If p equals 1, it's just 1 over x, which is like 1 over n. We know that one diverges. And if the exponent here is larger, it makes your denominator that much bigger. And if you've got a bigger denominator, then your fraction's obviously smaller. And just like here, we just integrated this one with a 7 and it converged. Right? So we had a p greater, this is a p right up here. The p is the exponent right there. That's greater than 1 and it converged. Any number greater than 1, it will converge. And if it was greater than or, less than or equal to 1, then it would diverge. We talked about these way back when. The same thing applies to series. So that's what it talks about on page 118. If you flip back to where we just were, at the top of page 124, it talks about a p-series. A p-series is a series that looks like this. I'll squeeze it in this corner, right underneath this. A p-series is anything that looks like this. Guess when it converges?
It's greater than this one.
If p is greater than 1, right? Because if the integral converges, then so does the series. Where did y come from? Don't ask me. P greater than 1. So the nice thing about p series is if you can notice that you just have a power of 1 over x to any number, if you can just say, hey, I recognize that, that's a p series. And it either converges or diverges because p is equal to whatever. So this particular problem right here, instead of doing the integral test, you could have said it's a convergent p series. P is equal to 7, which is greater than 1. Oh, now my 7s and my greater than look the same. My problem today. My B's and my 6s look the same. My 7s and my greater than. Gotta make it this kind of 7. There we go. Doesn't help. So you should be able to do the next one just by looking at it. Example 2b. Just by looking at it. He says p equals 1/2. That's a square root, right? Well, it's positive 1/2. The p series has the x to the p's in the denominator. Yeah, diverges. Let's write it up here. N equals 1 to infinity, 1 over square root of n. So Chad says that is 1 over n to the 1/2. Why is it diverging?
Because
The p is not greater than 1. This is a divergent p series. You need to tell me you know what p is, and you need to tell me that it is less than 1, right? Don't assume that I know that you know what p is. If you're going to tell me it's a p series, tell me what p equals. And then whether it's greater than or less than 1.
greater than or equal to 1 is convergent.
It converges if it's greater than. Because if it equals 1, it's the harmonic, which diverges, right? So we usually don't talk about the 1 because the 1 is a special case, it's the harmonic, but it diverges for greater than or equal to 1. So it only converges if p is greater than 1. Which I think kind of makes sense because you can see your denominators are going to be that much bigger, which means your fractions are that much smaller, and then therefore it will converge faster. Is the next one a p series? 2c? You don't think so?
Yes.
Yes? Ooh, I got yes, I don't think so. Anybody want to go with a no? Oh no, I'm just taking all the possible answers. To C, n equals 1 to infinity. My question is that a p series? I heard, I don't think so, and yes. And it's not n to the third to the tag. If it was times n, I'd agree with you.
Can you do 1 over n and then parentheses n plus 1, and then that would make p 1?
So factor the denominator?
Yes.
Like that?
Yes.
So I still don't think it's a p series, because if it's a p series, I can write it as 1 over x to some power. I can't do that. I can't put those together. I can't just say it's n to the, did I say x? There should be an n. I just caught that. You guys catch that? I put an x in here instead of an n. Right? Should be an n when we're talking about series. N. You guys got that? I put x accidentally. I heard myself say x, so wait a minute. So I can't write it as 1 over n to the p. I don't know what that is. It's not just the power of n. There's other stuff going on there because of that addition. So it's not a p series, darn it. We were just getting happy with those. We can just look at the numbers and answer the question. Could I, do an integral test? Here's a review question for you. If I wanted to integrate this, what technique would I need? Ooh, somebody said
That
it.
A over.
Yeah, the A over
Yeah.
something, or whatever. We need partial fractions.
That's me.
That's no fun. But let me give you our little segue before we go to our break. Do we agree that this expression, 1 over n squared plus n, is less than, I have to make sure I say that right, less than 1 over n squared? That's a true statement? Why?
Because the denominator is always going to be larger on the left side.
Right, this one has a larger denominator, so it's a smaller fraction. Right, bigger denominators have smaller fractions. Agree that's true? This is less than this always? Pick an n and plug it in if you don't agree. Put a 1 in there. This will be a 1 over 2, this will be a 1 over 1, that's smaller. Put a 3 in there, whatever you need to. But because this denominator is larger, that makes the fraction smaller. These are the same. What can you tell me about this series? That one's a p-series. This is a convergent p-series, I just heard that. Why is it convergent? He's greater than 1. Convergent p-series. P is equal to 2, which is greater than 1. Well, this series converges. So what do you think is true about this series? Think it's less than this one? Can I just bring that down and make it less than? Is that true? We've already said up here that every term here is lower than every term here. So when I add these all up, this needs to add up to something smaller. Right? I mean, because everything's smaller than that. What does convergent mean? Convergent. The numbers in the series approach, when you add them all up, they approach some total, some limit. So when I add these all up, let's say they all add up to 5. I don't know what they add up to, it's probably not 5. Let's say they add up to 5. What do these add up to?
Something less.
Something less than 5. Do you think it converges or diverges? It has to converge, right? Because it adds up to a number that's less than 5. There's no way it could diverge, because diverge means it adds up to infinity. If it's smaller than 5, or whatever this adds up to, it has to converge. This must converge. This must converge by what's going to happen after our break, by what's called the comparison test. One more test to throw into this. Put yourself a little star next to that. It's the next section. We'll do that after the break, the comparison test. But the comparison test is nice because when you have things that are ugly, it looks like a p-series but not quite, or it's a messy integral. If you can compare it to a series that you do know what happens, then it's really easy to tell if it does or doesn't converge. We'll do that after the break. I'm going to pass back your exams and we'll take a 10-minute break after that. Somebody will come back at 2:10. This is a summary of all the tests that we're going to be talking about for all of Chapter 11. It puts them all in one place. We haven't learned them all yet, so some of them won't make sense, but we're going to be adding to them in the next few weeks. The very first one where it says nth term test is actually the divergence test. So if you want to change nth term to divergence, that will make more sense. So the first half of this should look fairly familiar. If you change that first word to divergence, this says it diverges if the limit of the general term is not 0, what we talked about earlier. Notice what it says, if it is 0, it's inconclusive. It doesn't say it converges if you get 0. The geometric series is next, so it talks about when it converges and when it diverges. Shows you the formula for finding the sum. P-series are on there. converges if p is greater than 1, the same thing we've just been talking about. And there's some little notes on the side, which will make sense after we talk about the comparison test. The integral test is on there. And then from there on, everything else is new. The comparison test is right where we left off. I just erased it. That one where we talked about, we had that kind of ugly one, but we said it's smaller than a convergent series, so it must have converged. So you're going to want to use this for reference, but you don't want to rely on it. You want to get to the point where you recognize how they're all kind of tied together and how what they're saying is very similar. Because if you're going to ask me if you can use it on the test, the answer is no. But you will have it all in one place. You can use it on your quizzes. The whole point is to recognize what it means to be convergent and divergent, and once you understand that, whether you want it to be greater than 1 or less than 1 should make sense. And if not, then you're going to ask me questions. Okay, so the comparison test is next. Comparison test on page 127. At the very top, I have some summary there to remind you of the divergence test and the integral test. That's usually if we start the day there. Because we've already been talking about them, I'm not going to fill those parts in. But you might practice yourself later. Write down what the divergence test tells you later. Write down the integral test. But let's talk about the comparison test. I'm going to jump right in with example 1. Oops, let me change my title here. We're not on the integral test anymore. 11.4. Which color is it? Oh, I don't like this black. It's dying. Comparison tests, plural, there's 2 of them. One is easier to work with than the other, but messier, so it's hard to say which one you like. So let's just jump in with example 1, so we can talk about it. I have this series n equals 0 to infinity of 1 over 3 to the n plus n. Question's always the same. Does it converge or diverge? It's not always the same, but it's almost always the same. Does it look familiar? Does it look like anything we already know?
Similar to the P series,
Kind of like a P series? What makes it like a P series?
the n, 3 to the n.
Okay, so a P series, I just erased it. I better write it over here. A P series doesn't have the n as your exponent. A P series is
The geometric was.
1 over n to the p. That's an n. That's a horrible n. Let's fix it. 1 over n to the p, so n is raised to some power. So if you had said this part's kind of like a P series, n to the 1, that's kind of like a P series, but that's really the harmonic if we just look at that part. But this part's not P series. What'd you say, Joseph?
The geometric series.
Yeah, so we're kind of looking at different terms. If it was just this, that'd be the harmonic series. If it was just this, you agree that's geometric? What's your R? If it's geometric, R is 1/3, right? Just keep multiplying by 1/3 over and over and over again. Which of these terms in the long run do you think counts more? This one or this one? Which one's bigger in the long run? Yeah, the 3 to the n, the exponential gets bigger way faster than this. So this is one that counts in the long run. So I would like to compare it to this series. I'm going to compare it to that one. Is this series bigger or smaller than that one? This series less than or greater than this one?
Less.
Less than, again, for the same reasoning, right? Because the denominator is larger. Less than. Tell me about this series. This one, on the right. Tell me about the series on the right. What can you tell me about it?
That one converges.
Why? You can't just tell me it converges. I want to know why.
Because R is less than 1.
Ah, it's geometric. and r equals 1/3, and absolute value of 1/3 is definitely less than 1. So you have to tell me you recognize that as geometric and you know what r is. That's all you have to do for that one. It's geometric. R is 1/3, converges because r is less than 1. Convergent means this adds up to some number. We could actually find what it adds up to. We have a formula for geometric.
First term.
We could take the first term, which is 1, oops, we started at 0. First term is 1. 1 over 3 to the 0. Over 1 minus r. That's 1 over 2/3. That's up to 3/2. So if I were to list all of these terms and add them all up forever, I would get 1.5. You don't technically need to find the sum, just a little review for you. Everyone understand what this means? What can you tell about this series then?
It is also convergent.
It's also convergent, why?
Well, it's by comparison, it's gotta be less than 3x.
Yeah, when I add these all up, it's gonna be less than 3/2. Is that infinity? There's no way, right? If you're less than 3/2, these are all positive. You're gonna add a bunch of positive numbers, get an answer that's less than 3/2. So this one has to converge by the comparison test. Converges by the comparison test. Because if you're smaller than a convergent series, you add up to something less than it does, which means you must converge. Yes?
What is that therefore symbol?
Therefore, 3 little dots in a triangle form. Therefore, converges by the comparison test. But if this problem was on the homework, you could just write this, and you'd get full credit, because you've shown me what you compared it to. Now, I came up with that on my own. I said I'm going to ignore that part and use that part. We'll talk about how to choose what to compare it to in a minute. I referred to this one, explained why it was convergent, and then I said this one must also converge by the comparison test. So we'll talk about what the comparison test says. It says, suppose you have 2 series, one's an AN and one's a BN, 2 different series. So for example here, this might be AN and this might be BN. I was talking about 2 general series. It says that if BN is convergent and AN is less than that, then this one must also converge. That's exactly what we just did here and with the previous example before the break, right? This one is convergent. These terms are smaller than those terms, so therefore this one has to also converge. And the smaller than only has to be eventually smaller. Some series are weird at the beginning, like it's a little bit bigger, but eventually it's smaller because of the way the terms are working. If it's eventually smaller, then it will work. Smaller than a convergent series means it's convergent. Now that's the first part. If AN less than BN, I'm going to write it up here, and we know that BN converges, then the series for AN converges as well. 2. Oh, it's not 2. Does that make sense? Why it has to be smaller than it? Well, the second line says, well, what if BN is divergent? What if the one series, the second series, is divergent? And look at this one. AN is greater than or equal to. I left off my or equal to over here. Less than or equal to. But they're equal would be good. So what does it mean for this series to be divergent? What does divergent mean?
Goes to infinity.
It adds up to an infinitely large number. So these terms add up to infinity. And these terms are bigger than that. So if you're going to add up to something bigger than infinity, guess what you're adding up to?
More infinity.
More infinity. I like that. More infinity. So what's going to happen?
Divergent.
It's going to have to diverge. So if you're smaller than something convergent, it kind of forces you to converge because you're stuck going to something that adds up to a concrete number. But if you're bigger than a divergent one, you add up to even more infinity, so you must diverge. That's what we're looking at, the comparison test. It's important that you understand what the words converge and diverge mean, because then you know it adds up to infinity or it adds up to a number, then it makes more sense why you want to be less than or greater than. Questions there? Okay. The reason we do comparison tests on this, like generally we compare to, usually we compare to make things easier and nicer and more recognizable. We compare to a geometric series, or we compare to a P series, or we compare to the harmonic series. We compare to something we know, usually when your series is really messy. Like the one we had before the break was kind of messy, this one was kind of messy. Usually that's when you're going to do a comparison test. So let's look at my next example. This is example 2A. We want to know if this series converges or diverges. 6 to the n over 5 to the n minus 1. So we want to know if this series converges or diverges. We could do the divergence test. I'm glad you recognize that. We could do the divergence test. Turns out it won't be 0. But let's say we forgot the divergence test just for the moment, because we're practicing the comparison test. Divergence test would have worked here, though. So I should compare it to another series.
Geometric series.
Yeah, maybe a geometric series that looks a lot like it. In the long run, but it's not going to really matter in this one. Yeah, that minus 1's not going to make much of a difference in the long run. So let's compare it to this series. 6 to the n over 5 to the n. Is our series bigger or smaller than that?
Bigger.
Bigger? Why is it bigger?
Because there's a minus one denominator, so there's no going to be smaller.
Beautiful. Denominator on this one's a little bit smaller, which means the fraction's bigger. When your denominator's smaller, the fraction's bigger. What can you tell me about this series?
Because it's divergent.
How do we know it's divergent?
Because it diverges.
They're G.
Okay, but we're not doing the divergence test right now.
No, I'm just saying that's like.
Okay, I know.
Ours is less.
It's geometric though. I'm practicing the comparison test. I'll agree with you, the divergence test tells you the same things. We agree with this series? That makes it a geometric series. This is a divergent geometric series. Because R equals 6/5, and the absolute value of R is greater than 1. Or you could have used the divergence test, it's approaching infinity, so it's not 0 when it diverges. So it's a divergent series. The series that we're interested in is bigger than this one. What does this one add up to? Infinity, that's what it means to diverge. This one adds up to an infinitely large number. This one adds up to a bigger infinitely large number. So what happens to this one? Diverges. Therefore, this one diverges by the comparison test. obvious what you want to compare it to either. But usually you throw out some constants that in the long run don't really matter, and you look at the things that will still be hanging around with the ends get really big. It's not always, it takes a little bit of practice. Questions there? Okay, let's look at 2B. I don't know if I corrected these on yours when we printed them at the printers or not. Do you have a minus sign on the top or not?
What?
N
Positive.
squared plus 2 or minus 2?
Plus 2.
It's supposed to be a minus 2, so let's fix that typo. So 2B, mine has a little note here to correct it, and apparently it never got corrected. N equals 1 to infinity, it should be an n squared minus 2. Right there, that minus, you guys see that? Change that, otherwise it's a little bit trickier. Oops, n to the 4th plus 5. Plus 5. I get this. Everyone got the correction, minus 2? Do you think it converges or diverges? What's your gut tell you and why? Your gut can be wrong, I'm fine with that. You think it converges? Why? Because the denominator what? More than the top? Yeah, how much more is kind of the question. So he says because the denominator is so much bigger than the top, it's approaching 0 for sure. And it seems like maybe he thinks maybe it converges. I think I agree with that. What series is this similar to in the long run?
N squared over.
N squared over n to the 4th, right? Because in the long run, you put infinities in there, the minus 2 and the plus 5 aren't going to do much. So I'm going to compare it to the series of n squared over n to the 4th, which is 1 over n squared. Just simplifying. How does our series compare to that one? Is it bigger or smaller?
Pretty small.
Smaller? Why?
Because the denominator is larger.
The denominator's larger and the numerator's smaller, right? So both of these, this makes it smaller and this makes it smaller. Well, that's a less than here for sure. What can you tell me about this series? Yeah, Evelyn?
It's a D series.
It's a D series.
It converges because the P is greater than 1.
P equals 2, which is greater than 1, so it converges. That one converges. What does that tell you about ours?
Ours also converges.
Also converges. This one converges by the comparison test. When you're doing the comparison test, you're really doing 2 problems in one every time. You have to compare it to something, and you have to explain what that something, that new one you came up with, you have to tell me what that one does and why correctly. And then, once you've decided that, you can tell me what yours does. You can't just assume that I'm psychic and that I know what you know. It's all in your head and I can't see it. Okay. Let's look at C. And not freak out too much because it looks all weird. And then we'll talk about what to do when the less than and greater than don't work the way you want. Because they don't always work the way we want. So this is C. We have this series here, n over n squared minus cosine squared n. Cosine freaks you out a little bit. What do you know know about cosines? What kind of answers do you get when you take cosines?
Between zero, 1 and 1.
Yeah, a cosine's always between -1 and 1. The highest you can get is 1 and the lowest you can get is -1. So if you square it, it's always going to be positive. I mean, you're going to be subtracting something between 0 and 1. Just from what we know about cosines. Right, we're subtracting something between 0 and 1. So in the long run, that term right here, or this term right here, doesn't do much. It either subtracts 0 or subtracts 1 or some little fraction in between. But once you're at, you know, 1 billion squared, subtracting 1 or something close to 1 doesn't make much difference, right? So what do you think I'm going to compare it to?
N over N squared.
N over N squared? And if I compare it to that, is mine less than or greater than that? Less than? Because
Because the denominator is always going to be smaller.
the denominator of this fraction is smaller,
If it could be 0, couldn't it be the same?
then it would be the same. But if the denominator is smaller, does that make this fraction bigger or smaller than this? Yeah, we're having a little controversy. Look, greater than, right? I'm glad you corrected that. Greater than or equal, right? Because it could be 0. There's certain n's that it might give it exactly 0. But because my denominator is smaller, the fraction is bigger. What series is this?
We could do G series.
We can call it a P series, but I think we would need to simplify it first.
Harmonic.
It's the harmonic series. It's also a P series. If you simplify this, that's 1 over n. What can you tell me about that series?
Divergent.
It diverges because
Harmonic.
you could call it P series or harmonic. Divergent. Harmonic series. The harmonic series is the only one that you can just say, it's the harmonic, it's divergent. That's just a fact that we're going to use. So you could say it's a divergent harmonic series, divergent because it's the harmonic series. But Joseph wants to call it a P series. Is it a P series?
Yes.
Yeah. P is equal to 1. Is that less than 1?
It's less than or equal to 1.
Ah, but it only converges.
So like,
Oh, I didn't finish writing it. Only converges if P is less than 1. Is that P less than 1? No, so it diverges, which makes sense. It still has to diverge. So you could either say it's a divergent P series, or it's divergent because it's the harmonic series. Yes, sir?
The notes that you gave us says it converges if P is greater than 1 for P series, and diverges if P
Sorry.
is less than or equal to 1.
I was trying to make that point and I wrote that backwards, so let me paraphrase that. That's true. My brain, I was worried about the or equal to. So it only converges when P is greater than 1, but not when it's equal to 1.
That's why I said when it's equal to, it would be backwards.
Right, so I said it backwards, I apologize. Now, who else did I confuse with that? Miss-
wait, so you said just if P is greater than 1,
P is greater than 1,
then it diverges.
less than or equal. Why do you want it to be bigger than 1? What does it do to the fraction if your P is
Makes
bigger
the
than 1?
denominator smaller.
Make the denominator bigger and the fraction smaller, right? So that makes more sense that you want P to be larger for it to converge. I apologize for writing it wrong. Doesn't have to explain it. So you could have said it's a divergent because it's a harmonic series, or you could say it's a P series and P is not greater than 1. This one is divergent. The one we're interested in is bigger than that, which means
It's also divergent.
it's also divergent. So this one is divergent by the comparison test. So these have all been fairly straightforward in terms of what you want to compare it to. It works out nicely. But sometimes they don't work out nicely. For example, 3A. We'll talk about the test above it here in a second. Oh, it's right above 3A actually. The next one says consider, it's written there. It's going to be 3A.
Let's write this one out and talk about why it's weird. So right after example C, we have this guy. N equals 0, oh, my pen's dying. I must have switched. 3n minus n. And off to the right, I even have a comparison there. Makes sense that in the long run, you would just compare it to 1 over 3 to the n. Because in the long run, this term is so much bigger than that term. Exponentials grow much faster than lines. So I'm going to compare it to this. Is our series greater than or less than that?
R is the less than,
Oh, this one. I just want to know to put a greater than or a less than symbol here.
It's great.
It's greater than. Why?
Smaller.
Denominator is smaller, makes the fraction bigger. Right? The denominator always does the opposite, right? Okay, so that's good to know. Tell me about this.
P series.
It's not a P series. Not a P series. P series looks like this. I don't have n raised to a power. It's geometric. It's geometric because you can write it this way. Right? It's geometric. R equals 1/3. Does it converge or diverge?
Converge.
It converges. Because the absolute value of 1/3 is definitely less than 1. That's good to know. So that means it adds up to something. We can find the sum if we wanted to. It like adds up to 2 or something like that. I can't do it off the top of my head. It adds up to something. What about our series?
R is greater than.
Ours is bigger than that. So let's say this adds up to 2. If this adds up to 2, and ours adds up to something bigger than 2, do we know what ours does? Does it converge? Does it diverge? Some of you are giving me this, I don't know. Everyone understand the problem? Bigger than 2 could be that it adds up to 8, which means it converges. But it can also add up to something infinitely large, that's bigger than 2. So when you're larger than something that converges, you really don't know anything. Right? If you say it's larger, it could be just a little bit larger or it could be infinitely larger. We don't know that it converges or diverges. Not enough information. Which is why the comparison test only talks about being smaller than a convergent one or larger than a divergent, because otherwise you just don't know. Same thing would happen if you were smaller than something that diverges. Maybe you're still infinitely large, but a smaller infinity? I mean, we don't know. So this doesn't help. Comparison test doesn't work here. I want to make sure everyone understands why it doesn't work. We have something larger than a constant. Larger than a constant could be a bigger constant, could be infinity, we don't know. So this is why we have the limit comparison test, which is what's next in your notes. The limit comparison test is actually easier to work with in that you don't have to figure out the greater than and less than stuff. You can do some algebra sometimes to do the right comparison. Because I really think that my series converges. I really do. Even though it's bigger than something that converges, I think it converges because in the long run, I think it's going to behave a lot like that guy, even if he is slightly larger. See what I mean by in the long run? It's a little bit bigger, but I don't think he's enough different that it's not going to behave the same way. So the limit comparison works when you have two series that you're pretty sure behave the same way, but you can't force the one to be greater than or less than the way that you want it to work out. So what it says is that when you have your two series, your AN and your BN, so in this case, here's my AN, and here's my BN. It says that if you just take the limit of those two terms, oops, I don't want to write it out for that one yet, of your AN over your BN, it doesn't matter which one's bigger or smaller. If that limit is some constant, then those two series will both do the same thing. They will behave the same way. So the way it's written in our notes, it says that if you have your AN and your BN, and if the limit of those two is a constant, the constant has to be positive and finite. Can't be infinite, it's not a constant. Can't be zero. Can't be zero, it has to be positive, constant. If that's true, then they either both converge or both diverge. If this is true, or both diverge. I like to say they behave the same. Let's talk about that positive constant. If I take the ratio of one to the other and get a constant, that's just telling me that maybe this one, let's say the constant is 7. That means this one is 7 times as big as that. That's what that constant would mean. If it's 7 times as big, and this one converges, this just converges to something 7 times larger. Or if this one diverges, then it's 7 times infinity, which is still divergent. So the constant is just showing you that you have picked something where they behave the same. One is a multiple of the other in the long run. So I can't make this less than. I wish it was less than, because my gut tells me it converges. But this tells me nothing. So instead, I'm going to do the limit comparison test, which will look messy, but it's fairly easy. I'm going to take the limit of this term divided by that term. The 1 over 3 to the n minus n over 1 over 3 to the n. One term over the other. If I get a constant, if I get an answer, not 0 or infinity, feeling pretty good. I'm going to flip this one over and multiply. That's 3 to the n over 3 to the n minus 1. So this one got flipped over and multiplied. Gets rid of your fractions inside of fractions. What's that? Am I something? Oh, I missed an n. Thank you, Dan. 3 to the n minus n. Thank you. You guys see that? My n turned into a 1. How do I take this limit?
Three of the ends cancel.
They don't really reduce now. But they do kind of come to play, but they don't reduce. What form is this in right now? What's the top go to? Infinity. What's the bottom go to? Oh, what do we do when we have infinity over infinity? Oh, we can do L'Hopital's rule. We love L'Hopital. He's our buddy. Then we have to remember how to take the derivative. 3 to the n times the ln of 3. Whenever it's something other than e to the x, you have to multiply by that. 3 to the n times the ln of 3 minus 1. This is another way we could have done this besides L'Hopital, the shortcut. I have to do L'Hopital's again, is why I asked. I'll tell you after we do L'Hopital's again. If I take the limit again, or the derivative again, I have 3 to the n times ln of 3 squared now. So I'll have to multiply by another ln of 3. and I have 3 to the n times ln of 3 squared minus 0. That's a mess. What's it equal to? 1, right? 'Cause 1. Limit equals 1. Anything over itself equals 1. My shortcut would have been right here. Just look at the highest powers. In the long run, those guys are going to outweigh that n. So your limit's going to be the highest powers do. So what does that tell me? This limit of those two equals 1.
It's finite, so it converges.
That's a finite constant, so they both behave the same. We already talked about this one. It's a convergent geometric series. So what can you tell me about our original one?
Converges.
It converges by
Limit comparison.
the limit comparison test, which I didn't write up here. I said it, but I didn't write it. Converges. Limit comparison test. Let me write that on the board over here by the description of it. Positive constant. This was the limit comparison test. Now, a lot of people don't like it because it's messy, you've got fractions inside of fractions when we do it. But it's actually much easier than the comparison test a lot of times because you don't have to worry about greater than or less than. You just need to make sure you're comparing it to something that is similar. The most common question I get is, what happens if it's 0? What if I did the limit and I got 0? It's not finite, it's not positive. Well, it is finite, but it's not positive. What do you think it means if you take the limit and you get 0? If I took the limit of this over this and got 0, that means that one on the top was so much smaller than the other one that the limit was 0. It means it's a bad comparison, is what it means. If you don't get a positive constant when you do the limit comparison test, it's because you didn't pick the right one to compare it to. You might get 0, you might get infinity, which means that they're nowhere near each other. So sometimes you have to try something and it doesn't work, and then you try something else to compare it to, and then it goes from there. I put my notes down, we're out of time, but I think I only had one more example of limit comparison, we were good? Oh, and then the last one was a segue into how the limit comparison doesn't work anyhow. So example B, what do you think you would compare it to? Let's just talk about that in the next 20 seconds. What would you compare example B to if you were doing a comparison? N over n cubed, which reduces to 1 over n squared. Right, so just look at the highest powers and deal with that. And then you can just take the limit and see that they should behave the same. The last one we can't do anyhow, we'll talk about it on the next time. I think you should be good. I got one more paper to give you before you leave. It's a very specific list of how and what you should write when you're doing these and why notation is important. I'm going to give it to you now, we will discuss it next time.
Do you want 11.2 and 11.2?